The next type of problem we want to solve is our bullet and ring problem, where an object collides with another object that can rotate, and we use the initial velocity and the mass of the bullet and the properties of the ring to find the final angular velocity. This problem is a good bit like the apple and the arrow problem we did several units ago, where we start with our arrow that has all of the momentum. Then after a collision, we have a new combined apple and arrow that is moving together with a new momentum. So we're going to do this problem in a general way, and then in the problem that you guys are going to do, you're going to do the same thing with the SI units with kilograms and meters. So in this problem, we have a ring that is rotating counterclockwise with an angular velocity of omega and a mass of 20 m. It is then struck by a bullet that is traveling to the right, and it hits the bottom of the ring as shown here. We want to find the angular velocity as a function of the initial angular velocity of the ring and the velocity of the bullet. So first we want to find the direction of the angular momentum. For the ring, it is rotating counterclockwise, and so using the right-hand rule, we find that the angular velocity vector is pointing out of the page, so we will call that positive. For the bullet, it's also moving counterclockwise when we look at the where it hits the ring, so it's also positive. That means the sum of the two, so they're both positive, so we add them together, so that means that our final angular momentum is going to be positive as well. Now we want to find the angular momentum of the ring and the bullet. The ring is pretty straightforward. The moment of inertia is mr squared, and the mass is 20, so the moment of inertia is 20 mr squared. And then we multiply that by the initial angular momentum, omega, and so we get 20 mr squared omega. For the angular momentum of the bullet, we can find it two ways. One way is that the angular momentum is the radius across the momentum, so it is the radius times the mass times the velocity. So we can also find it because the moment of inertia is mr squared, and the angular velocity times the radius is the velocity. So omega is equal to the velocity over the radius. This also gets us mr squared times v over r, so one term of the radius cancels, so again we get mvr. So in your case, I think you're going to find the moment of inertia first, so that's going to be mr squared for your bullet, and then you can use the mvr to get the moment of the angular momentum. Now we want to find the final angular momentum, and this is the moment of inertia of the bullet plus the ring. So this is 20 mr squared for the ring, and mvr for the, it's for the moment of inertia, my bad. So it's the 20 mr squared for the ring and mr squared for the bullet. So that means that the final angular momentum is going to be 21 mr squared times the final angular momentum. So angular velocity. So now we want to find the final angular velocity in terms of the initial omega and the velocity. So to do this, so the total angular momentum is the results we found on the previous slide. So there, for the ring, it was 20 mr squared omega, and then the angular momentum of the bullet was mvr, and we set that equal to the total angular momentum final, which is 21 mr squared times the final angular velocity. So essentially at this point, we can then isolate the value for the final angular velocity. So this becomes 20 mr squared omega plus mvr divided by 21 mr squared. Okay, so this one requires a few steps. So on the next question, you're going to walk through a similar problem, but here you're going to put kilograms and meters into it rather than doing it in general like this one. Also in the homework, I think you're going to have a similar problem that uses a kid jumping on a merry-go-round. It's really the same problem, but we're just using a kid instead of a bullet and a merry-go-round instead of a ring. I guess it's a disc, not a ring. All right, good luck.